Hey everyone! In this video, we're going to be looking at how to find indefinite integrals by using the method of substitution. Now, the method of substitution is something that takes a lot of practice. So what we're going to do is run through several examples, and as we go through the examples, I'm going to talk about a few things that I like to think about to help me through this process. So my first example, I have the indefinite integral of the sine of 3x plus 2 times dx. So the way it stands right now, I don't have an antiderivative rule to help me find the integral of this expression. But I do know how to find the integral of just the sine of x, for example. So what we can do is we're going to use substitution to rewrite the expression a little bit and make it easier to find the antiderivative. So in this example here, what I'm going to do is I'm going to let u, so the variable u, I'm going to let this equal everything inside the parentheses on the inside of sine. So u is going to be equal to 3x plus 2. So that will allow me to replace everything that's in here, and then what I'll be left with is the sine of u, which I do know how to find the antiderivative of that. With the method of substitution, the other additional thing we need to do is replace the dx here. So to do that, we are going to find the derivative of my expression for u. So if we take the derivative of u, so du, we can just use our standard derivative rules. So the derivative of 3x is just 3, and then the derivative of 2 is going to be 0. And since we're taking the derivative with respect to x, we have a dx here. So now I want to get dx isolated. So I'm going to divide both sides by 3. So what I end up is 1/3 times du is equal to dx. So setting that all up, I have u, which I can replace for the 3x plus 2 here. So that x can get replaced inside the parentheses. And I also have an expression that I can substitute in for dx. So what we end up with, now we're going to have the integral of the sine of u, and then instead of dx, we'll substitute in 1/3 times du. So one of the properties of indefinite integrals, I can take this constant factor, I can bring that out front. So I'll rewrite this as 1/3 times the integral of the sine of u du. So that's essentially the method of substitution. So we replaced some things in our original expression so that we end up with something that we do know how to find the antiderivative of. So the antiderivative of the sine of u, that's going to be negative cosine. So we still have our negative 1/3. Now the antiderivative, that's going to be negative cosine of u. And since we are doing an indefinite integral, I need to include my constant, so plus c. And now the last step, we need to undo our substitution. So I know what u is equal to, so we'll resubstitute that back in, and we'll get our final integral here. So negative 1/3, and then cosine, and then resubstituting for u, we'll plug in 3x plus 2, and we still have our constant term. And there's our final answer. Now, if I wanted to double check this, I could take the derivative of my final expression here, and I should end up with what we started with. In this case, the derivative of cosine is going to be sine, negative sine, so the negatives will cancel out. And then we're using the chain rule, so we would multiply by the derivative of the inside, which ends up being 3, which would cancel out the 1/3 here, so that does look like everything works out. So in this first example, just to kind of re-summarize what I was thinking about there, looking at what we started with, this expression was more complicated than what we knew how to find the antiderivative of. But since we knew how to find the antiderivative of just sine of a variable, we can use the substitution to replace what's on the inside of the sine and make it a little bit easier. So now let's move on to the second example. Here I have the integral of x cubed times e to the x to the fourth times dx. So this one's a little bit different, but again, just looking at it right away, I don't know how to find the antiderivative of that expression. So we want to use substitution to rewrite it into an expression that we do know how to find the antiderivative of. In this case, when I'm looking at it, I have two different factors that are being multiplied together. I have an x cubed, and then I have my exponential term here, e to the x to the fourth. If I take a look at my two x's here, I have one that's x to the fourth, and my other one is x to the third. Now looking at those, if I take the derivative of x to the fourth, the degree goes down 1, so I would end up with something with x cubed. So I like to keep an eye out for those situations, because then when I do my substitution, since we take the derivative of our expression for u, we know that we should be able to replace everything we need here. So let's let u equal x to the fourth. And then when I take the derivative of this, so du, this is going to be equal to 4x cubed, so just the chain rule, and then times dx. So hopefully you can see here that after I take the derivative, I do end up with my x cubed. The only difference is this constant factor out front. So why don't we divide by 4? So 1/4 du is equal to x cubed times dx. So now taking a look at what we started with, I know what u is going to be, x to the fourth, so I can substitute that in here. And then the other two places we have an x, the x cubed and the dx, we can replace both of those with the 1/4 times du. So why don't we take care of that? So let's do our substitution. So in my exponential term, instead of the x to the fourth, we'll substitute in u. And then replacing the x cubed and the dx, we have the 1/4 times du. And just like we saw in the last example, I can take this constant factor, I can bring that out front. So 1/4 times the integral of e to the u power du. So again, we were able to use substitution to rewrite this as a simpler expression that we do know how to find the antiderivative of. The antiderivative of the exponential, e to the u, is just itself. So we have 1/4 e to the u power, and since we're doing an indefinite integral, we have our constant plus c. And just like the last example, we'll undo our substitution. So we'll back substitute in for u, which was x to the fourth. So we have 1/4 times e to the x to the fourth power, plus our constant term plus c. And there's our final answer. And again, if we wanted to double check that, we could take the derivative of our answer, and it should match with what we started with here. So now the first two examples we did kind of cover the two main things that I'm always looking for when I'm doing the method of substitution. In the first one, I looked at the expression and I said, I do know how to find the antiderivative of sine, so I wanted to rewrite it so that I could end up with just the sign of a variable. And in the second example, we looked at it and we saw that if I replace x to the fourth, the derivative of that would be something with an x cubed. So there's a little bit of a relationship there, making it easy for our substitution. So now let's keep those in mind as we go through these other two examples. So in this one, the integral of x times the square root of x squared plus 1 times dx. So here's another situation where if I take the derivative of what's underneath my radical, so the derivative of x squared, the degree goes down 1, which would give me an x to the first, and then the only difference would be some constant factor out front. So let's let u equal x squared plus 1, and if we take the derivative, du is going to be equal to 2x times dx. And just like our last example, let's divide by 2 to take care of that constant factor. So 1/2 du is equal to x times dx. So just taking a look at this, everything underneath our radical, that will get replaced by just u. And then the x and the dx, both of those can get replaced by 1/2 times du. So let's do our substitution. I'm going to put the 1/2 out front right away. So just taking that constant factor out of the integral. So we have 1/2 times the integral. And then underneath our square root sign, we have the square root of u. And then x and dx, we have the 1/2 out front already. And we have our du. So I'm just going to rewrite this. Instead of thinking about it as the square root, I'll think about it as u to the 1/2 power. And then here we can just use our normal antiderivative rules to find the antiderivative of u to the 1/2. So if we do that, we're going to increase the exponent by 1, which will be u to the 3/2 power. And then to make sure this simplifies properly, we need to put a 2/3 out front. And again, we have our constant plus c. And then to finish up, we'll resubstitute. So I can simplify these fractions as well. The 2's will simplify, so we're just left with 1/3. And then resubstituting for u, we're going to have x squared plus 1 to the 3/2 power, and our constant plus c. And here's our final answer. So let's take a look at one more example, just going through that process again. So the integral, and I have this fraction of 3x plus 3, and that's divided by 2x squared plus 4x, and then we have our times dx as well. Here's another situation where if I take a look at the denominator of this fraction, I have an x squared. If I take the derivative of x squared, that degree goes down 1, which would be something with just an x to the first in it. So I'm going to say, let's let u equal 2x squared plus 4x. If I take the derivative of u, I'm going to end up with 4x plus 4, and that'll be times dx. Now taking a look at this, it doesn't really match up with what we have in the numerator in this fraction. So the way we set up u, the entire denominator will be substituted for just the variable u. But now trying to replace dx and the numerator here, it doesn't really match up with what we found for the derivative of u. So we might have to work with this a little bit. One thing I do notice is in my derivative here, I can factor out a 4. So I'm going to divide both sides by 4. That's going to give me 1/4 du is equal to x plus 1, and I still have the dx here. So x plus 1, that's a little bit simpler, a little bit easier to work with. And now if I compare that to what I have in the numerator, I have a 3x plus 3. Those have a common factor of 3, so why don't we factor that out? So I'm going to bring that 3 out front. So factoring that out, we have 3 times the integral. If I factor that out, my numerator will be x plus 1. And then I'm going to keep the denominator the same because we already know that that whole denominator is going to get replaced by u. And we still have our dx. So now taking a look, the denominator, we can substitute u in for that whole expression. And then the numerator, we have x plus 1 and the dx, which we know we can replace with 1/4 du. So we're going to have 1 over u, replacing the denominator. And then substituting in for the x plus 1 and the dx, we have 1/4 du. Let's take the 1/4 and move that out front. So we have 3/4 times the integral of 1 over u times du. So just like we've seen in the other examples, using the substitution and rewriting the original expression into something that's simpler and something that we do know how to find the antiderivative of. The antiderivative of 1 over u, that's going to be the natural log. So 3/4 times the natural log of the absolute value of u, and we have our plus c, our constant term. And to finish up, let's redo our substitution. So 3/4 times the natural log of the absolute value, resubstituting in for u, 2x squared plus 4x, and our constant term plus c. And here's our final answer. So overall, a couple things that we can look for and we can use to help us figure out how to do the substitution. We can look at the expression and we can think about what we do know how to find the antiderivative of. We did that in the first example where we know how to find the antiderivative of just the sign of a variable. So we want to use the substitution to get to that point. And in the other examples, we were looking at the expression overall, and we were breaking it up into basically two parts. We have one part where we can substitute, and then we know that taking the derivative of that, it works out to give us the other piece in that expression. For example, in this one, if I take the derivative of 2x squared, I get down to something that's x to the first, so the substitution works out nice. Now, as I said in the very beginning, the method of substitution is something that just takes a lot of practice. But overall, if you do a couple of these, you start to notice patterns and things that work. And oftentimes, it just helps to just jump right in, try something out, just take a guess and see if that's going to work for the substitution. And a lot of times, it will work. And if it doesn't, it'll lead you in the right path to actually find out what will work for the substitution. So hopefully running through these examples helped you out and you were able to learn a few things on how to use the method of substitution to find indefinite integrals.